2.5 billion times. So if you divide it to all the people, let's say on the world, then I guess 1/5 has one. 200 are actually in use right now, I guess, 200 million. And it has a proprietary stream cipher which is called Crypto1. The key length is about 48 bits. That's, well, it looks small, but actually you only can talk to it over, let's say the air, over the R4D channel. And well, then makes it a little bit harder. If you do not know the cipher itself, then you can only try to brute force it online, and that's quite hard. There's some piece of memory actually where you can store something and you can wipe it away, and you can, it's just like a very small USB stick, I guess. And then it carries also a unique identifier, which was originally the ID of RFID. You have radio frequency identification, so it's the ID of the card, which shows like, oh, I'm this one. And well, they invented like, oh, it's maybe nice to store some memory in it, so you can store more chips or something, or your value amount which you have on your prepaid transport ticketing card. Well, it's nice to see the under square. It's like in their documentation they say field proven. Well, that's quite nice, but let's see what it actually means then, for security at least. What it is a hardware chip. And you have to use the hardware chip. Well, that was originally the case. For that, you needed a reader and you needed a chip itself. Then you can talk to the chip like, okay, I want to talk to a Mifare card. And then the chip will has 2 pins connected to an antenna, and then it will use the antenna to communicate to a Mifare card, and then it will communicate to the microcontroller or the computer in the back what it has communicated, well, at least what you wanted to request. You have to give a key, and then it gives you the answer. But the problem is here that you do not know what the chip does. The chip does some fuzzy things over the air in the field, but you only know that it's actually communicating to the card, but you do not know how or where or when. Well, this was it's maybe a fuzzy slide. It shows lots of fields of memory, sectors and blocks. I guess it's a little bit boring to go into this, but it's nice to see that you have like lots of keys on a card. You have not one key, but you have different keys for multiple applications on a card, and then you can say, well, one is a write key, one is a read key, and well, if you configure that a nice way, you could have very interesting applications, which I did not see in the field actually, but it was possible. Then I'll go to what are really the security features? And these are not really all of them, but I guess the most important one, what they claim to be, or what they actually said, like, what is the security here? Now, they have, of course, that fixed unique identifier. I have to say that's a really manufacturer burnt-in identifier, so you cannot really change that. You cannot really change later on in a test stage. Well, at least that's what they say. So, and I was never able to do it. So until now, I have some reason to believe it. But then you have a mutual authentication. The thing is there. The reader is identifying. I know the key to communicate, and the tag is identifying back to the reader. Oh, but I know also the key. So both identify to each other that they know the key. There are random challenges, like, okay, you have a really, you need some randomness in the cipher, which is, otherwise you could do the replay attack I showed earlier, and that's, that's boring to even have in your product. Now, then there is a proprietary non-public algorithm, which is, I guess, it was non-public, but at the moment it's a little bit different. I'll come to that later. The thing is that you have also encrypted communication, but it's encrypted with a proprietary algorithm which no one should know, and it is embedded in a chip, so you cannot really look at it or even reverse some EEPROM. You really have to look at the hardware side. Well, then there are some other measures to it's like teasing other manufacturers. Like we make a protocol and we make it ISO compliant, but in the end we change it slightly that it is not ISO compliant anymore because we are sending weird parity bits, which are on network level, well, good defined, but they are used in a different way. Well, that's the hardware implementation. I noticed that already. And oh yeah, there was one more thing to say. They said, well, it's maybe nice that only once the card will send a random number in the clear, and after that it's all encrypted. Wouldn't that be secure? Well, I'll come to that. Here's an Oyster card. It shows on the screen what it actually does. You keep it in the field, it transmits, the reader actually gives a signal, and the card answers with its own code. On the card you see there is 10 pound and some key, which the reader of course knows and the card knows. With those combined you get some kind of well, the transaction actually made, and it's communicating the algorithm, using that crypto1 algorithm, the encrypted stream back. But the thing is now that this is all happening, but it was all not open and not secure. So we are all like, well, what is with this product? What are the commands to do? I mean, the chip is going to talk to the card, and it gets some answers, but what is it actually saying? Well, if we strip away the encryption, I mean, it should ask like, I want to read something or I want to write something. So that was a challenge. And then we tried to find out what is the authentication about, and what is the algorithm actually? Are there obvious weaknesses? Are there some biases? Are there side channels? Are there maybe other cryptographic mistakes? Well, it's very nice because they were. What we started at our university, we use the Proxmark device I showed earlier. It's the most advanced device we have, and it's actually working pretty well because you can listen to a very low level, and you can even see both sides communicate to each other and then look into what they're actually saying. But the thing is that this is the university entrance, so it's our own door access control system. And, well, that was nearby, so we actually wanted to know what was on our own employee pass, so we just started to toy around with it. Well, what we did is actually tracing. You see there on the left, you see a very simple Omni key that's a commercial reader, and it's a Blanco card you can buy on eBay for less than €1. And, well, in the middle you see an antenna, which looks very, very home and hobby made, but it's actually working very well. So what you see in the other on the bottom there is a trace. Well, it's in hexadecimal values, and it shows some of the things that happened there. I've commented a little bit, but I'll go into that later what it actually means. But you see here that it authenticates, it gets a random number, the tag, the nonce tag, is a nonce of the tag, of course, then. It's a random number from the card to the reader, and then you have the reader, which actually also gives a random and answers to that random from the tag, and then the tag answers again to the back to the